Hello, everyone. And yes, everyone. So today I'm going to talk about the basics about RLC circuits. And this will involve differential equations. So yes, yeah, hopefully this is going to be useful. I have recorded slightly more on the more advanced side last year, so you can watch those if you are if you understand, if you have very good understanding on what of the things that are going on in an RLC circuit, then feel free to watch those. Today I'm going to focus on the just like on the logic behind, like why is it and what, and somehow A level have been avoiding these circuits, which is not great, which is not great. And we'll start with the Lenz's law. Okay, we'll start with the Lenz's law. So basically, if you move a magnet into a coil, the coil will react by producing a current that is in the opposite direction. Somehow, that's what they say. You know, when you're talking about when you talk about Lenz's law, they say the current is induced in the opposite direction. So let's look at these examples. So you have a coil, and you have a magnet moving into the coil. And as the magnet moves into the coil, the magnetic field in the coil increases. The field, or the flux in the coil, increases. And because we know the field from the magnet goes this way. This is the field from the magnet. So a current will be induced in the coil in order to counter that. So the current in the coil would be in a direction such that as to oppose the change that induced the current in the first place. So there's a field there's a field from the magnet in the coil that goes this way. So the coil will produce a field in the opposite direction. So the black lines is field from the magnet, and the blue lines is the field from the coil, Do you understand why the direction of the field is like that? Do you understand both directions of the fields? Please let me know in the chat. One, two, three more people. Yeah. Okay. All right. So good. So would you like me to go through the other two examples, or are you fine? Basically, I'm asking, do you understand the Lenz's law? And would you like me to go through these two examples? I think we're good. Okay, just to get a feel of the room, because I've had a chat with one of you before, and okay, right. So when you like, if you have a circuit, and a battery, I mean, and a lamp, for example, when you close the switch and you draw the graph of current, sorry, time, and this is the current, and it's supposed the current should go like this, 0 0 0 0, and then suddenly drops, pitches up, and then like this. I mean, at least that's what theory tells you. I mean, does it actually go this way? Because this thing always baffled me. Like before I learned about inductance, like why it can't just step up. I mean, in physics, nothing ever just steps up, right? Even when you hit a ball with a bat, the speed doesn't go like this. It increases gradually. Yes, so it should go something like this and like this, right? So it like never it never goes just suddenly from 0 to something. And the effect is magnetic, of course, is the Lenz's law. The Lenz's law is responsible for this. And you don't see it with normal everyday conductors. With an everyday conductor, it goes like this. And let's have a look. So we have a battery and a resistor, and like this. And we switch on the switch, and you can see the step. Once again, it's 0 0 0 0, and then bam. So you can see the step. This step is theoretical. It never actually happens that way. And to see what was going on, we can place an inductor. And we place an inductor. And you can see that the graph takes this shape. The inductor slows down the change in current. It prevents rapid change. It does that by producing a voltage in the opposite direction. So whilst the current is changing, a voltage is induced in the inductor. So this is plus, minus, plus, minus, plus, minus. So the inductor acts as a battery pushing in the opposite direction. And you can use Kirchhoff's law, and this is V1 and V2. EMF is equal to V1 plus V2. And V1 is IR. So EMF is IR plus the change plus the voltage on an inductor. And the voltage on an inductor is L di dt. Now, they tell you that the voltage on the inductor is minus L di dt. So why did I put a plus? Why did I put a plus here? Well, for the same reason I put a plus for IR, because IR is a drop in drop in voltage, right? So why did I put a plus? Well, I put a plus because it makes sense. I'll see if you can understand. Sometimes you will have a complicated circuit and it would be difficult to figure out whether you need a plus or a minus. L is positive, of course, because that's the inductance, and di dt is also positive because the change is positive, so it's increasing. And I know that this has to be true. This has to be true where E is positive, V1 is positive, and V2 is positive. And therefore I've just copied this down. So I'm using the modulus in a way. I hope that makes sense. I mean, you have a circuit, and you could be strict, and you could say that EMF is an increase in potential, minus V1 is a drop, minus V2 is also a drop, equals 0. But then again, okay, V2 is a drop. Do you put it as a plus or a minus? You see, you always have this question in front of you. In practical applications, you just need to do a sanity check on yourself. Like, is it going to be plus or minus? And then you use that. So you almost can ignore the Lenz's law here, which tells you that there's a minus, because you can work it out. You can work it out for yourself. Is it going to be positive or negative? And then based on this, put a plus or a minus. Okay, I hope that makes sense. Okay, so I'm going to delete that, and then you can see that this is a differential equation. This is a differential equation in terms of I and EMF, and we can solve this. L di on dt is equal to minus IR plus EMF multiply both sides by dt, multiply it by dt, and divide by minus IR plus EMF, L di over minus IR plus EMF equals dt. And we can integrate minus IR. We can integrate, and I changes from 0 to, well, the final current is going to be EMF over R, assuming the resistance of the inductor is 0, from EMF over R, and time changes from 0 to, well, t. T is the time, because we need current with respect to time. Actually, no, sorry. What am I doing? Sorry, ignore me. Current changed from 0 to I, and time changes from 0 to t. And so L, and then if we integrate that, it's going to be minus 1 over R multiplied by logarithm minus IR plus EMF between limits 0 and I equals t. If we integrate that, it's t. And then we have minus L over R logarithm. So we plug in I, logarithm EMF minus IR minus logarithm EMF. And that's equal to t. Now, we need to figure out, because there's a modulus, we need to figure out which is bigger, EMF or IR. Well, IR is always slightly less than the EMF, because you can see that I approaches the maximum value, but it kind of never reaches it, at least mathematically. So we can drop the modulus. It's going to be plus. So EMF is always greater than IR. Therefore, we just combine the two, or we just drop the modulus sign. So minus L over R, and it's going to be logarithm EMF minus IR divided by EMF. Oh, there's no modulus, sorry. Brackets equals T. So E minus IR over E is equal to E to the power minus R over LT. And EMF minus IR equals EMF E R over LT. And I is equal to EMF minus EMF E minus R over LT divided by R. Or in other words, current as a function of time is EMF over R minus EMF over R E minus R over LT. This is this is the current in the circuit, and this is the graph that we got. The shape of the graph here is exactly that. This is the equation. And does it make sense? Does it? Because it looks like it's going to be When t is 0, it is 1. Oh yes, it does make sense. Makes perfect sense. Okay, so that's the graph. And that's the explanation for that graph. And okay, this is what. Oh, I've solved this exact example here. Okay, and for an LC circuit, basically what the inductor does, the inductor prevents change in current. So if the current is increasing, the inductor will try to decrease it. And if the current is decreasing, the inductor will try to increase the current. It works in the opposite way. We could also say that the inductor stores energy. The coil stores magnetic energy. And when you switch the current on, some of the energy from the battery is transferred to the resistor, but some is transferred to the coil. And as time goes by, the current in the coil gets bigger and bigger and bigger. And once it reaches the maximum, now all the energy goes into the resistor. So kind of the inductor kind of drains some of the energy from the battery. Compare this to this circuit. Yeah, something like that. At first, so the current has a choice. So the current leaving the battery has a choice whether to go through the resistor or go through the capacitor. And because the capacitor has zero resistance, you would have a lot of current flowing through the capacitor. Okay, so at the start, all the current will go through the capacitor and no current will go through the resistor. And then as the capacitor charges up, as the capacitor gains charge, the current, well, the voltage, the V1 is equal to V2 always, right? So as the capacitor charges up, the voltage on the resistor increases and the current through the resistor increases. So you could say that the capacitor drains energy from the battery, but as it fills up with electrostatic energy, then the energy is now redirected to the resistor. Okay, so hope that makes sense. And the most interesting, like the next circuit, I find it incredibly fascinating, and somehow they completely ignore it in A levels. Is the LC circuit? LC circuit with a capacitor and an inductor. The capacitor is charged. Let's say the top plate is positive and the bottom plate is negative. And now it will discharge through the inductor. But remember, inductor doesn't like change. At first, the inductor will produce a voltage in the opposite direction. And that means the capacitor will not discharge instantly, because if there's no resistance, right? There's no resistance, so it should discharge instantly, but it doesn't. The capacitor prevents rapid change in current. So it will most certainly will prevent infinite current. But then the current as a function of time the current will increase, then to reach a peak and then start decreasing. But when it starts decreasing, the inductor will try to keep it going for longer. It doesn't like change. It doesn't like a drop. So it will produce more current. It will produce a voltage in the opposite direction, pushing the current. So when the capacitor has discharged, the current in the inductor is a maximum, and it will keep the current going. The current will flow until the bottom is charged. The bottom is positive and top is. So effectively, we're switching the charge. So let's have a look. Let's have a look. We take a capacitor and an inductor. We'll need a switch and another switch. Okay, so first we'll charge the capacitor and measure the current. Now I'm going to switch on this circuit. So the capacitor will discharge through the inductor. So the capacitor discharges through the inductor, but then the inductor because the inductor has stored magnetic energy, it pushes the current further to charge the capacitor in the opposite direction. You can see that the polarity of the capacitor is constantly changing. So positive, negative, negative, positive. So I don't know, I find it really fascinating, this circuit. And let's do the differential equation here. Okay, so we know that the voltage on the capacitor is equal to the voltage on the inductor. So voltage on the capacitor is equal to the voltage on the inductor. The voltage on the capacitor, we already know that this is V equals CV. No, Q equals CV. So Q over is the charge on the capacitor divided by the by the capacitance. Yes. All right. And the voltage on the inductor is L di dt. Okay. Now the signs. If the capacitor is charged positively, then the inductor will produce a voltage in the opposite direction, so plus and minus. So they have the same polarity, so that makes perfect sense. And the change in current is positive, so yeah, that works. Okay, but current is also the rate of discharge of the capacitor. So it's minus dq dt, because current is how fast the capacitor is discharging. So I can plug this in here. So Q over C is equal to L. D, so because I is the derivative, okay, so minus dq dt squared. And this is a differential equation of the second order. And we've actually seen this. So dq dt squared equals minus 1 over LC times Q. Does this equation remind you of anything? Yes. It's the second derivative. Well, this is the second derivative of Q is equal to minus 1 over LC Q. SHM. It is. It is SHM. And we know the solution to this equation. We know the solution to this equation is x is equal to a cos omega t plus phi is a solution. So for this one, Q equals amplitude multiplied by cos omega t plus phi is a solution. And because we're talking about the charge on a capacitor, the parameters can be determined by the initial conditions. So let's say if the capacitor is, well, let's use the real thing. Capacitance is 0.1 farads. So capacitance is 0.1 farads. Then the inductance is 5 Henry. Inductance is 5 Henry. The initial charge, well, the initial voltage is 9 volts. V0 is 9 volts. And what else? I think that's all we need. Okay, so the initial charge, Q0, is the initial charge is V0 divided by C, which is 9 divided by C, which is 0.1 farads. So it's 90 coulombs. Well, that's a capacitor. Okay, that's a massive capacitor. Anyways, 90 coulombs. That's fine. 90 coulombs. That means when t is 0, Q is 90 coulombs. So we can work out Q is equal to A, well, 90 equals A multiplied by cos 0 plus phi. And because we know that this is the maximum, and that means phi has to be 0 because 90 is a maximum. Because if it's not a maximum, because cosine 0 is a maximum value. All right, so we have phi 0. A has to be 90 because you can, if you solve this, 90. And omega is, turns out it's square root of LC. So that is square root of 5 multiplied by 0.1, square root of 0.05, which is approximately what? Square root of 0.05, 0.224 seconds to the power minus 1. Okay, so now we can write down the equation. Q is equal to 90 multiplied by cos 0.224 multiplied by t and phi 0. So that's the equation of this curved line, which we've established. Let's see. Well, that's current. So let's do the current. Why not? So current is the derivative of that. So current is dq dt minus dq dt, because it's the rate of discharge, and it's, we use the chain rule here. It's going to be 90 times 0.224 multiplied by sine 0.224t, which is 90 times 90. It's going to be 20.1 12 sine 0.224t. Yes. Oh, I see where I got wrong. Yes, I was wondering. Yes. So, okay. It's 1 over LC. Thank you. W is 1 over LC. And that means that it is 1 divided by L, which is 5 times 0.5, which is square root of 2 is 1.41. 1.41. Still doesn't make any sense. 1.41, 1.41, 90 times 1.41. According to this, the current should be 126.9 amps, which obviously isn't. So let's see what's going on here. 1.1. The maximum current is about 1.3. It sounds like it, but not 100. So what went wrong? I think we got the frequency is wrong. Voltage is 9. So did I mess up? Did I mess up? So the capacitance is charge divided by voltage. The voltage is Q over C. So that's yes. The initial charge was wrong. Q is CV. CV0. So it's 0.1 times 9, which is 0.9 coulombs. That's more realistic. And 0.9. So this is A is 9. Oh, 0.9. Sorry, 0.9. Q is 0.9 coulombs. So 0.9 equals A 0.9. And this is 0.9, 0.9, 0.9. So it's 1.269. 1.27. 1.27, 0.9. Okay, that makes more sense. And you can see that the current, a maximum value of 1.27, and it's this. Yeah. So, and it is 1.27, and the omega is 1.41. So we need the time period. The time period t is equal to 1, so 2 pi divided by omega. That's the formula. So it's 2 pi divided by 1.41, which is approximately 2 pi divided by square root of 2, which is 4.44, 4.44 seconds, the time period. And let's have a look. Does it seem right? Well, half a period. So this is 1 second. So half a period is about 2 and something. So 2 seconds. It looks like it is, because you can, if you look here, so this is 1, 2, 2.2. So this is about 2.2 seconds. 2.2 seconds, and so it makes sense. All right, so let's look at problem 4. This is the, we're talking about the same circuit. Right, so we have a switch, we have a capacitor, and we have an inductor. So capacitance, inductance. The capacitor is initially charged. So let's say this is plus, this is minus. So the initial charge on the capacitor Q0 is 200 microcoulombs. The capacitance is 0.18 Henry, and the capacitance is 8 microfarads. Maximum current. Determine the maximum current. Right. So we need to find, well, we need to find Q. So we write down the equation. And it's the same equation. Like we don't need to invent anything here. So we write down that V1 is equal to V2. So V on the capacitor is equal to voltage here. This is Q over C is equal to minus D2Q over dt squared L. And we know the solution. Q is A multiplied by cos omega t plus phi. Now, at t equals 0, Q is maximum. And it's equal to 200 microcoulombs. That tells us, so 200 equals A multiplied by cos 0 plus phi. And that means that phi is 0. Because it is a maximum, and cosine is maximum when phi is when this expression is 0. Oh, it could be 2 pi. And therefore, A is 200 microcoulombs. Once again, and omega is 1 over square root of LC. And this is 1 divided by square root. L is 0.18 multiplied by C, which is 8 times 10 to the minus 6. So we're going to have 1 over square root 0.18 times 8 times 10 to the minus 6. 833. 833. This one. Okay. All right, so what do we need to find? The maximum current. Well, to find the current, we differentiate dq dt with a minus, because the current is the rate of discharge of the capacitor. And, well, I mean, it's arbitrary. I mean, switch the ampere around, the ammeter around, and it's going to be positive. So it's not exactly correct to say it's minus because it's the rate of discharge. I've chosen it to be negative because of that. And okay, so I differentiate that, and using the chain rule is going to be A omega sine omega t plus phi, and therefore I max, the maximum current, is when sine is 1, so it's A omega, which is A, which is 200 microcoulombs times omega 833, and that gives us times 200 1.67 times 10 to the 5, but microamps, so divided by million. So it's 0.167 amps. That's the maximum current. Okay, and then what are we? The time period and frequency. So A is the maximum current, B time period. Well, we know omega, so we can work out time period. Time period is 2 pi divided by omega, which is 2 pi divided by 8v3. So it's approximately 7.54 times 10 to the minus 3 seconds, and frequency is 2 pi. It's omega divided by 2 pi. So 1 is 133 hertz. 133 hertz. Okay, that's the frequency. And last question, energy stored in the capacitor and the maximum energy stored in the inductor. Well, energy stored in the capacitor, energy in the capacitor is 1/2 CV squared, which is 1/2 multiplied by the capacitance is 200 micro multiplied by V squared. We don't know V squared. Let's use a different formula. 100 CV squared, which is also equal to 1/2 Q squared over C. I think that's correct. Q squared over C. Yes. Q squared over C. So that is 1/2 multiplied by Q, which is 200. Okay, yes. No, I haven't embarrassed myself yet, but I was about to. Q squared is 200 micro squared divided by C, which is 8 micro. So it's 1/2 multiplied by 200 squared times micro divided by 8. So 200 squared divided by 16. You can notice that I'm using micro as a well, as an object. Yeah, I'm using micro instead of 10 to the minus 6. I'm just leaving it here, 200. It's useful. 200 squared divided by 16, 2,500 microjoules, and that is, of course, 2.5 millijoules. 2.5 millijoules. All right. The energy in the inductor is 1/2 L multiplied by I squared. So it's 1/2 multiplied by L, and L is 0.18. 0.18 multiplied by the maximum current. The maximum current is 0.167 squared. All right, so 1/2, 0.5 times 0.18 times 0.167 squared, 2.51 millijoules, which is approximately 2.5 millijoules. And this should not come to a surprise to you, because when the capacitor is charged, it stores energy. And then when it discharges, when charge on the capacitor is 0, the current is maximum. So the energy of the inductor is maximum. So all the energy of the capacitor goes into the inductor. And then from the inductor, it goes back into the capacitor. So it goes from the capacitor to the inductor, inductor to capacitor. Right. Okay, what affects the frequency of the oscillation of the circuit? So you've seen that omega is 1 over square root of LC. That means frequency is omega divided by 2 pi. So that's 1 over 2 pi square root of LC. Or time period is 2 pi divided by omega, and that is 2 pi square root of LC. It's very useful. They're very useful to remember. I think the time period is the easiest formula. So the time period is 2 pi square root of LC. Compare this to time period is equal to 2 pi square root of LG. And time period is equal to 2 pi square root of M over K. Do you recognize all of these formulas? Yes or no? Do you recognize these formulas? Okay. So this is the time period of a pendulum. And this is a mass on a spring. On a spring. So these are useful. These things, they are familiar to you. Now, let's focus on this. So what affects the frequency of the oscillation? What are the two factors that affect the time period and hence the frequency? Well, it's L and C. L and C. Let's say you want to have a circuit with a very high frequency. To make a high frequency circuit, we need low inductance and low C. Okay. Are you on board? Are you on board with me? We need low. Do you understand that to make a high frequency circuit, you need low capacitance and low inductance? Do you understand that? Okay. Let's look at capacitors. If you look at the capacitor, look at the capacitance, is 0.3 picofarads. Let's make the plates bigger. What happens to the capacitance if I make the plates bigger? The capacitance increases. If I make the plates smaller, the capacitance decreases. Right? Making plates bigger, capacitance increases, decreases. If we separate the plates, if we move the plates closer, the capacitance increases. And if we move the plates further apart, the capacitance drops. So what do we need to do to the plates of the capacitor? So we have a coil. And we have a capacitor. What do we need to do to the capacitor? We need to make the plate smaller and further apart. Okay? So we move the plates further apart. And now you make them smaller. Well, you can move them. All right. You make them smaller. Well, how far can you go? Well, you can go like this. Make plates smaller and further apart. Plates smaller and further apart. How do we reduce the inductance? How do you think we reduce the inductance of an inductor? What do you think? What makes an inductor more inductive and less inductive? Remember, less coils. Yeah, okay. So we make fewer coils. Well, how do we make it minimum? Well, we just have no coils. Reduce number of coils. So, and make the plates just nothing. What is that? What does it remind you of? What object does it look like? No, it's not no L and no C. It has what? Well, not just a wire. What is it? What does it look like? I mean, nowadays these things don't look exactly like that. Yeah, an antenna. It's an antenna. An antenna is a high frequency oscillating circuit where the tips end of the antenna acts as a capacitor and the wire acts as an inductor. Any wire will have an inductance. It's just the fewer the coils. With no coils, you still have inductance. It's just going to be very, very, very small. And the capacitance, because the ends are very, very far apart, the inductance, the capacitance is going to be very small. So we've turned an oscillating circuit with an inductor and a capacitor into an antenna. So this is a really high frequency, because if you look at the frequency, they are 800 to 2600 megahertz. That's a lot. And an antenna, well, yeah, we set up we set up oscillations in an antenna. We use a power source to set up an oscillations in an antenna. The current goes back and forth through the antenna, and it catches the waves, catches the electromagnetic waves coming from the um, coming from the well, the surroundings. So if you have an antenna, the current goes up and down. Current goes up and down through the antenna, and you have an electromagnetic wave passing through the antenna. And if the frequency of the wave if the frequency of the wave is approximately equal to 1 over 2 pi square root of LC, then you can then you have resonance. So we have resonance. So the current, the microcurrents in here turn into macrocurrents. The current increases. And becomes enough to produce sound through a loudspeaker. And that's how you listen to radio. Right? So yeah, that's how you listen to radio. You can have a earth, for example, here, and you can have a loudspeaker. I mean, it's a very simplistic view. This is a loudspeaker, and you connect it like this, you connect it like this, and yeah, that's how you can actually listen to a radio. And if you can look up inductance of a straight wire, you can see this is the inductance of a straight wire. So you can it does have any wire will have inductance, right? So it depends on the it's a non-zero inductance, even if it's just a straight wire. So yeah, these are the ideas behind oscillating circuits. What else did I want to mention? Oh, for these ones, you can model. You have a battery with internal resistance. The current through the inductor has stabilized. When the switch is open, the capacitor starts to charge and discharge due to oscillations of period t in the circuit. So let's model this. I mean, why not? We'll take a capacitor. we'll take a battery. The battery has internal resistance, so we'll model this by adding a resistor here. Okay, and let's make it smaller, slightly more realistic. And we have an inductor here. Oh, forgot the switch. Got the switch. And we have a wire, another wire. All right, so when I switch the current, of course, you will have the current flowing through. Okay. Let's just compare. So let's say we charge the capacitor. Can we charge the capacitor? Okay. Let's say we charge the capacitor. And now we discharge the capacitor through the resistor. So you can see the voltage is 9 volts. And yeah, the battery is 9 volts. So the maximum voltage has to be 9 volts. That's obvious. If you charge a capacitor to 9 volts, you can get 9 volts out of a maximum of 9 volts on the capacitor and on the inductor. So this makes perfect sense. But now I play a different game. So I disconnect this and all right, so I need to discharge the capacitor. So the capacitor is not charged. Now I switch the current on and you can see that there's a current flowing through the inductor. And because there's a voltage on the inductor, there must be a interesting. What is the voltage on the capacitor? Okay, the voltage on the capacitor is 0. All right. So the voltage on the capacitor is 0. But there's a current flowing through here. Now I disconnect the battery. And suddenly the voltage is 25 versus 24. How can we get such a high voltage from a 9-volt battery? You see what happened here? We started with a battery. We had a 9-volt battery. We connected to a capacitor. We let it go, and the amplitude of the voltage is 9 volts. That is a duh. It has to be 9 volts. But suddenly, if I first connect the battery to the capacitor, and then I disconnect the battery, suddenly the voltage spikes up into to 25. Let's see if I can get even more out of it. Let's say if I use a lower resistance, my prediction, if I use a resistance of 1 ohm, I'll be able to get an even higher voltage. Notice the capacitor is very slowly discharging. So I need to give it time. I mean, 0.09 volts won't make any difference realistically, but just for the sake of the experiment. Okay, now I disconnect the battery. And the voltage just goes crazy. 60 volts. I got 60 volts. That's quite fascinating. I mean, it fascinates me. So what's going on here? Well, because the battery is connected to the capacitor, to the inductor. There's a large current passing through the inductor. So the inductor stores a lot of energy. And when you disconnect the battery, all this energy suddenly goes into the capacitor. So it manages to charge the capacitor to 60 volts using a 9-volt battery. I believe something similar is used in a car, in cars. In petrol cars, you have a spark plug. And this spark plug it uses like a couple of thousand volts, I believe, like 2,000-3,000 volts. But you power it from a 12-volt car battery. So in a similar fashion, you get like 2,000 volts out of 12. So that's it. So what you need to figure out here is you need to figure out the energy stored in the inductor, and then translate it into the maximum capacitance. So it's quite straightforward. Find stored energy. Stored energy in inductor. Then find the corresponding voltage on capacitor. So that's my hint for this question. This is problem 11 from the assignment. Okay, I hope you enjoyed this. Type 1 if you've learned something new today, that it wasn't useless for you. And okay, that's good. That's right. Enjoying it, and yeah. So I'll see you next week. I don't have any guest speakers planned yet, but I am planning to plan some guest speakers. But next week you'll see me. All right, see you everyone, and enjoy your weekend. Welcome. I'm glad you like it. Happy to do these sessions.